Let me pay the TN. Okay, so I'm gonna skip chapter 27 of Schwartz. I think it's overly technical, and you know, if you're going to do QCD perturbation theory for living, of course you want to study chapter 27. But if you're not, that's probably not the highest, the most important thing in the remainder of the book. So I'm going to go to chapter 28, and I'm going to do the chapter 28 differently. I'm going to try to make it actually clear as a part, as opposed to partly cloudy. So I'm not going to follow it at all, actually. So let's talk about symmetries. And in particular, symmetries of the, first of all, symmetries of the action. The symmetries of the action would be, for example, you could have a discrete symmetry. You have a bunch of fields phi. If you can just multiply it by -1, that's an example of a continuous symmetry. So I will write the word discrete in case, what is her name? Ms. de Blasio is watching. Otherwise continuous, and now we have a gauge group. So I imagine that phi is a vector here, or that is to say an array, more generally, of points. And here I'm thinking continuous symmetry. And most of the time when one talks about symmetry, one talks not about the symmetry of the action, but the symmetry of the Lagrangian. An important exception is supersymmetry. In supersymmetry, you don't have the symmetry of Lagrangian, you have symmetry of the whole action, which is, of course, an integral d4 of x of the action density. And what happens is that the change in the Lagrangian in supersymmetry is a total derivative. And so you integrate it out, and then, for lack of funding, you drop the surface terms. Here, G of alpha is typically a compact Lie group. And of course, Lie group really means it depends continuously on the parameters of it. Okay. Alpha 1, alpha n. All right. Now, of course, not all symmetries are exact. Some are approximate. And we can say that among approximate symmetries, some are explicitly broken. So what is explicitly broken? That's when, for example, S of G of alpha phi is only approximately equal to S of phi. So we don't really have a symmetry. The thing is a little bit cockeyed. And an example of this is isospin. The up and down quarks are both very light compared to the scale of the strong interactions, which is what we call lambda QCD. And gosh, I hope I'm not skipping something. I did derive for you the beta function in QCD last time, right? Or did I not actually?
finished?
Just started. You haven't finished the duration.
I'm sorry,
I mean, you just started last time.
I just started it?
I think so, right? Just on that part of Blackboard.
Yeah,
Oh, God.
Yeah.
Okay, well, all right, but I've already started this. Let's do this then. I'm going to go through my spiel about the Higgs. Well, not the Higgs, about explicit symmetry breaking, spontaneous symmetry breaking, and the Higgs mechanism, although I don't know how far we'll get into that. And if I finish that story, then I'll run down to my office and grab the notes on the beta function, because I actually did write that up carefully after the lecture, and I just forgot about it. Okay, so isospin is an example, and MU and MD are much less than lambda QCD. These guys are around, they're less than 5 MeV in, the standard MS bar at normalized at probably the mass of Z. Whereas this guy here is 200 or 300 MeV. So we're talking about a factor of almost 100, about 100. And this shows up in the hadrons in that the mass of the proton is the mass of the neutron minus, I don't know, 1.3 MeV, something like that. Over C squared if we're in unnatural units. So that, I mean, that's 1 part in 1,000. That's 1/10 of 1%. It also shows up in the pions. So the pi plus and minus are about 139 MeV, and the pi 0, I don't know, it's 140. I may have them interchanged, but roughly they're within 1% or so of each other. Also, we have the K0 and the K plus or minus and the K0 bar. These are all around 500 MeV, and they differ from each other by, I don't know, 5 MeV or something, maybe 10. Anyway, so isospin is a symmetry that we say is explicitly broken. I mean, there could be aspects to it that we don't understand, and that these guys, I mean, because we don't really understand fermion masses, we just use the Higgs mechanism, and then we pull numbers kind of out of our nose to make the thing work out, and there could be a much better explanation. The other possibility is in which the action or the action density is exactly symmetric, but the particle spectrum isn't symmetric, and the reason is that the vacuum state is not unique. Instead, because the action is invariant, there is a symmetric set of vacua, and the actual vacuum is just one of them, and then you sort of expand perturbatively around that vacuum. But it's an arbitrary choice, at least we think of it as arbitrary. It may be because, you never know. Understanding could progress, although at the present Congress that's unlikely. But you choose one of the symmetric set of vacua, you expand about it, and such theories are said to be spontaneously broken. The actual terminology is not good, because the symmetry, and after all, symmetry is defined really in terms of the action, and the symmetry is still there. It's just that the vacuum is not invariant under the symmetry. The vacuum state. Under the symmetry transformation, the vacuum states move around. All right, so of course, normally we talk about the action density, and in this particular case, let's consider d mu phi I star d mu phi I minus b of phi, where by phi I mean the whole array of phi's, the n phi's. And let's suppose that this is invariant under a transformation. Phi I primes of x is a sum gij of alpha j equals 1 to n phi j of x. Notice that we're talking so far, and I'm going to be talking about global symmetries initially. So this is a global, we're imagining about a global invariance of L, of the action density. That is to say that L of G of phi is the same thing as L of phi. And of course, that implies that S of G of phi is S of phi. So the action for sure is invariant, the action density is invariant. But on the other hand, we're not sure about what's going on with the ground states. Now, one example might be, suppose the ground state is the case where all the fields are zero. Well, then the vacuum is obviously invariant under the symmetry, because no matter what G is, any old G on zero is zero. So the vacuum is invariant, the vacuum is unique, and so forth. On the other hand, sometimes the vacuum isn't at zero, and then you can have, under the group, the vacuum moves around, and the standard example is the case where V of phi, for example, is minus m squared phi I squared. Let us say sum I equals 1 to n, plus lambda over 2, sum on I 1 to n, phi I absolute value squared. And well, let's see. I wrote it in my notes as real. So here we have just n real fields. And now you see this is what people call a Mexican hat potential. I'm not quite sure why, but the idea is that you have this sort of sombrero, and if it rains, that's where the water collects. That's at the minimum of the potential. Okay. Now, and the complex case is sum minus m squared. Actually, if these things are real, then this is m over 2, and I suppose we have lambda over 4. If they're complex, then it's phi I squared plus lambda over 2, sum on I, phi I absolute value squared. And this guy is squared. I forgot to square it. All right. The minimum in these cases you obtain by saying 0 is partial of the potential with respect to phi squared, where phi squared is either the real thing or the sum of the absolute value squareds. And the way I've written it, that would be, let us do the complex case, which is like that. Then we get minus m squared plus lambda phi squared. And what I mean here is the sum of the phi I squared. And so I'm differentiating with respect to the sum of the phi I squared. And that then says that the sum of the phi I squared is m squared over lambda. And you notice the adroit choice of overall factors of 2, so as to get rid of them. Okay, so in this case, the minimum here has a radius here that's m over the square root of lambda. That's that r0. Distance from the center of the potential to the minimum would be m over square root of lambda. All right. So now, so let's speak more generally now that we have a potential v of phi, and for practical purposes, I'm going to be talking for a while about just global symmetries, and these symmetries aren't space-time dependent, so the derivatives don't get involved. This thing is automatically invariant. The kinetic part of the action is automatically invariant because it's a global symmetry. Okay. Because this thing is just as invariant as phi squared is invariant. So what we're really talking about is symmetries of v of phi. And what we mean is that v of phi is equal to v of g of alpha phi. So this is this is the symmetry. In other words, the potential and the action have an exact continuous symmetry. So there's an exact continuous symmetry of V, L, S, all of these things exactly symmetric. Okay, and the symmetry in particular is that phi prime of I is, let us put in the parameters, alpha, G of alpha on ij, phi j, sum j equals 1 to n if it's an n by n compact Lie group. And for alpha, after all, we usually use the parameterization e to the I ta alpha sub a, the exponential parameterization. I can never pronounce that word. It just has too many bloody syllables. And for alphas much less than 1, we say that phi prime I of alpha is, well, first of all, what's G? G of alpha is 1 plus I sum on A equals 1 to, and I don't want to use too many different variables. What's the number of generators? What are we going to call that? N sub G, number of generators. TA. Alpha A, and this is the n by n identity operator, and of course these generators satisfy, since we have a complex Lie group, compact Lie group, structure constant, totally antisymmetric TC. Okay, that's what we're doing. Now, Okay, so what we've got is that the vacuum, the potential is invariant, exactly invariant under the action of this group. So we have 0 is the change in the potential, and due to a change in these parameters, alpha. And so we're doing sum I equals 1 to n, partial v, partial phi I, change in phi I, and this is the sum I equals 1 to n, partial v, partial phi I, and the change in phi I, well, it's whatever you get from this, namely that phi prime I, or phi of alpha, say, is g of alpha ij phi j, and this is delta ij plus I sum ta alpha a ij phi j. Okay, so the change in phi I is then I sum ta ij alpha a. And so this thing is I ta ij alpha a phi j. Okay, so this is because the L is symmetric. All these words, the plasma is having an enormous effect on me. I have to send her an email, tell her to watch this. Okay. So this is the this is generally true. Moreover, we can differentiate again, and since we have something equals 0, its derivative certainly vanishes. And when we do that, we get 0 equals ij goes from 1 to n. Now partial 2 of v, partial phi I, partial phi k, I ta ij phi j. And here I was talking about a whole bunch of alphas. Well, we can have n different equations. You see, we're also summing over A here. We can pick out a particular A, and then what we've got is that A, and then we have phi j plus partial v, partial phi j, I ta I k, because we are differentiating here. Okay, so this equation is always true for any A and for any set of fields because of the symmetry of the potential. I'm delaying just a bit because I'm getting to a punchline. One of the students has left, and so I want to delay the punchline until he gets back. Does anybody have a question that could use up a few minutes?
This is a terminology question, I guess. Is there a difference between symmetry and invariance?
Yes.
Good.
Invariance means the thing doesn't change.
Right, Lorentz invariant.
Right, and here we're saying that the action density or the action doesn't change when you move the fields around according to a symmetry transformation.
Okay.
And so if you have a symmetry of the action, then the action is invariant under that symmetry transformation. So they're closely related in that way.
Okay.
Do you have a question? Or any hunger for some candy?
I'm a little bit wondering what happened to that alpha A
Good question. What happened to the alpha? All right, here.
I'm not following the algebra.
Okay. Well, up here, we had a sum over alpha over A. But it would equally be true that this equation is true for arbitrary alpha. Okay. All right. So suppose we have alpha 1 equal to 1, all the other alphas equal to 0. All right. Then what we get is this equation with A equal to 1. And A equal to 1 here. On the other hand, if we had this equation, which is true for arbitrary alpha, if we had the alpha such that it was alpha 1 was 0, and alpha 2 was 1, and all the others 0, then we get this equation with A equal to 2. Good question. I think we've blown as much time as possible.
So are you missing us?
Oh, another question. All right, hold on.
So are you missing another derivative of the second term, a partial?
I'm sorry, say that again.
Are you missing a derivative of the potential with respect to phi I?
On the second term, let me see where we are. You mean here?
Yeah.
No, because we're differentiating with respect to phi k, and we hit this guy. So when we differentiate with respect to phi k, we hit this guy and get d2. Yeah. We hit this guy and we just get delta kj.
Thank you.
Yeah.
Thank you.
Okay. So this was true in general because the action and the potential are symmetric. But now we set, I hope the Quasio will watch this, all these English words. Now we set phi equal to phi 0, one of the vacuum states, or vacuum fields. One of that minimize, more English words, that minimize the okay. Well, what happens? Well, if we set phi equal to phi 0, this guy vanishes because the potential has 0 derivative at the minimum. Okay. So, our equation is the second derivative at phi 0, and I can factor out an I, and what we have left is Pij phi j. But now phi 0 comma j. In other words, we have to substitute the vacuum value, a vacuum value, phi 0 here. And so that's equal to 0. Okay. Now let's look at the potential, or equivalently the action, near the minimum of the action density, the minimum of the potential. Because at the minimum of the action density, the fields are flat. They don't vary. Well, actually, if we're in Minkowski space, you could have big spatial derivatives driving the action density to minus infinity. So don't think about that. So what is the potential near the minimum? More English words. We have to get to quasi-dimensions. Near phi 0. V of phi is V of phi 0. The linear terms, of course, vanish because the first derivatives vanish. Instead, we have a half sum ij equals 1, or ik in this case for some reason, equals 1 to n, partial to v at the minimum, partial phi I, partial phi k, phi I minus phi 0 I times phi j minus phi 0 j. So that's what the potential looks like near the minimum. Okay. Now, this thing here, this second derivative is the mass matrix. And we can write that as this mass squared matrix. M squared ik is partial to v, partial phi I, partial phi k at the minimum. And of course, we're doing that at this particular minimum that we chose to expand around. So that's our minimum. This is an n by n matrix. N by n. It's real because they're derivatives of the potential. Okay, the student has finally returned. So let me, you can continue. Let me repeat, let me just say here, this thing is real and symmetric. It's consequently also Hermitian. And so it has n eigenvalues that are real. But let me just repeat this then, for the sake of the person who missed part of the talk. Because the action, or the Lagrange, the action density, or in our case just the potential, is symmetric, we have that the sum of the derivatives with respect to the change in the field under the symmetry, which are this in general, where we sum over the gauge parameters, or the group parameters, these are the generators of the group. This is the change of phi I, and this is the sum over I equals 1 to n, sum A equals 1 to the number of generators, whatever that happens to be. 3 plus U2, for example. Now, because of the symmetry, this is true always for any fields, any set of fields. And since it's 0, we can take a second derivative and we still get 0. So we get this relation here. Second derivative of the potential, and then the first derivative, because the derivative hits hardship. Now we go to the vacuum state, one of the symmetric set of vacua. Call it phi 0. When we go to that point, this guy vanishes because the potential is flat at the minimum. So we just have this. That equation then is 0 is second derivative at the minimum times the fields at the minimum value, TA, we're getting 0. And in fact, what I did here was I had originally the sum over A's. I just picked one A, so we have NG equations, one for each A. And the same thing is true there. Okay. Now, what we've got here is an n by n real symmetric matrix. This is the mass matrix. In other words, when you expand the fields about the minimum, and somehow I've reverted to real fields here. If we were talking complex fields, it would be v of phi equals v of phi 0 plus sum. And here, instead of a half, you just have this. Partial to v of phi, you have partial phi I star, partial phi k at the ground state, and then phi I minus phi 0 I star, phi k minus phi 0 k. And this thing should have been a k. I In some states, there's a law, you have to use INJ. But here in New Mexico, we use INK. Okay, so what we've got then is, in general, we're going to have n values of the mass. They're always going to be real, and in general, they're all different. But sometimes we get something special happening. And what's going to be special here is that, in general, you see, every combination of the fields, see this thing here, this is an eigenvector of the mass matrix with eigenvalue 0. Every one of them is going to have mass 0, with an important exception. So in other words, each of these guys, for every generator, in general, I'm going to get to the exception in a moment, but in general, for every generator, we have an eigenvector of the mass squared matrix with eigenvalue 0. So we start out with n sub g massless bosons. And again, I've been thinking about this in the case where all the phi's are real. In the case when it's complex, they're going to occur in pairs of the same mass. And so it may be n sub g pairs of massless bosons. And these things are called Goldstone bosons. Goldstone bosons. Named after Jeffrey Goldstone. I once rented his house, actually, for a summer. Anyway, so these are the Goldstone bosons. In general, you have as many Goldstone bosons as there are generators of the symmetry of the potential. Huge exception. Huge exception. The exception, of course, is that sometimes this thing inside the square brackets vanishes. And when it vanishes, we don't have an eigenvector of the mass matrix. We just have 0. And 0 times any matrix is 0. That doesn't mean that it's an eigenvector. An eigenvector with mass 0 is a non-zero vector that when multiplied by the mass squared matrix gives you something. It could give you 0, but it doesn't, if you get 0, it doesn't count if you start with 0. So there's a huge exception. And in particular, it's, one can think about it in two ways. The generators, of course, of the gauge group, we normally imagine that they came from, that they were written in stone on something that was found in Egypt or Israel or someplace, right? And that because of the dry weather, it's been preserved. But in fact, you can take any linear combination of these generators and you still have generators that are just as good and so forth. And if you do things correctly, you still have the same structure concept. So, the deal is then that, I'm not quite sure where I was going with that, but in any event, any linear combination of the generators that leaves the vacuum invariant, the vacuum state invariant, gives you a 0 here. Oh, that's right, that's what I was going to. In other words, if we go back to this, if we put the sum on A in here, now what we've got is we have better chance, we could put in alpha A. Okay. Now we have we can either think of this sum of TA alpha A as being, in other words, we could say T tilde A is sum TA alpha A. So we can just change with real coefficients. These guys are still Hermitian, they're still generators. They're just a different combination. And if you normalize them correctly, everything will work out. We could just as well say that this equation, instead of being a sum on A, was simply 0 is sum ij equals 1 to n, partial to b at the ground state, partial phi I, partial phi k, and we would have T tilde A ik no, it's ij actually. Phi 0j. Right. So this sum would be be the tilde generators. Okay, so the point is that if there's a generator that annihilates this vacuum state, then you don't get a Goldstone boson. So you get Ng unless T tilde A ij phi 0j equals 0. So in other words, what you have to do is you look at the symmetries of the action and or of equivalently the action density or the potential. So G is symmetry group of V of phi, the potential. Now, there's something called, typically one calls it H. This is the symmetry group of phi 0. In other words, there may be more than one generator that annihilates phi 0. And so, what shall we call these guys that annihilate it? In my notes, I didn't give them a nice name. Okay, we'll call them T sub H. T sub H, A, are the generators of G and of H, for that matter, such that THA on phi 0 is 0. So these are the ones that leave it invariant. In other words, e to the I alpha A TA sub H on phi 0 is 0. No, it's not 0, it's phi 0. So this forms a group of transformations, because if one linear combination leads to phi 0 invariant, and another does, the product of them also will, and so on. So it forms a subgroup. And in fact, this H contained in G then is a subgroup of G. It's a subgroup that that's generated by the generators that annihilate the vacuum. Or it's a subgroup that leaves the vacuum state invariant. So is there a question?
Yeah, if you pick a different vacuum state, will you have a different subgroup? Or for a particular field, does it stays the same?
Great question. Hand delivered, not hand.
First time.
In my experience, it's always the same subgroup. But, and I'll give you several examples, but whether there's some weird theory in which the subgroup somehow varies with the vacuum, that's that's interesting, and why don't you think about it? If you find an example, that may be a new physical mechanism. Okay, there might be something interesting in that. I mean, what's in a sense, we've already seen this, namely that if the vacuum is unique and its phi 0 equals 0, then the whole group annihilates, all the generators annihilate. But typically, it doesn't depend upon phi 0. There may be a case where it does. Okay, so basically, to repeat, you start out with an action density that's invariant of the global symmetry transformations. Because they're global, the only thing that counts is the potential, because the vacuum, the derivatives don't change at all under the transform. Well, they do transform, but they transform in a way that's symmetric. So it's typically an ON or a UN. And so you look at the non-trivial part, that's the potential, and you see that for every generator, you have an eigenvector of the mass squared matrix. And of course, the mass squared matrix comes from expanding the potential up to quadratic terms about the minimum phi 0. For every linear combination of generators, you get, or for every generator, I should say, you get 0. You have an eigenvector of the mass squared matrix at 0, but as long as this thing isn't itself 0, and if it's 0, then you don't have an eigenvector of the mass matrix with eigenvalue 0. So basically, you have every time you do have an eigenvector, you have a massless boson that's called the Goldstone boson. And for the other cases, the generators annihilate the vacuum or leave the vacuum invariant. Those guys can still have mass. So now what I want to do is I want to give you 4 examples, and I think we just have time we certainly have time to do all 4 examples. So let me do example 1. Single complex field. The potential then is V of phi is m squared phi squared plus lambda phi to the 4. The vacuum is phi 0 equals 0. The group G equal to U1 leaves V of phi and phi 0 invariant. So we would say that the subgroup that leaves the vacuum invariant is the same thing as the group itself, and consequently, we don't have any Goldstone boson because there isn't any generator that doesn't annihilate the vacuum itself. Or equivalently, the thing is already annihilated, and so when you construct this, it's not that the T's annihilate the vacuum, it's that the vacuum's already dead. Okay, so this is a field. You have 2 massive bosons, anti-mass M, and it's the boson and the anti-boson. Well, that's example 1. Example 2, of course, is closely related. Now V of P is minus M squared P squared plus lambda over 2 p to the 4th, and I stuck in a 2 because I want to have the mass nice. Now, the minimum, this is the Mexican hat potential again. So the minimum partial v partial phi squared is equal to minus m squared plus lambda phi squared. So the mean value of phi squared at the vacuum value is m squared over lambda. So now what do we have? Now we have a whole set of vacua, phi 0 of theta equal to e to the I theta m over square root of lambda. So now we have a continuous set of vacua. The invariance of the potential is U1, so the group G is U1. And the symmetric set of vacua is a circle, which also in a sense is U1. And on the other hand, if you take some group element inside this, then G on phi 0 of theta, if G is, say, e to the I phi, times e to the I theta m over the square root of lambda, then this is e to the I theta plus phi m over the square root of lambda. And so now this is G0 of theta plus phi. So the vacuum is not invariant, and so the group of the subgroup that leaves it invariant is 0. And so that means then that we have one Goldstone boson. In other words, how should I say this? If we look at the vacuum, if we expand the near, let's see, what did I do? Let's see if I have the example a little bit more. All right, we could imagine that phi 0 is simply m over the square root of lambda. And now if we add to that phi 0 plus delta phi that's real, then what we have is m over the square root of lambda plus this delta phi. And now what happens? This thing, the potential rises if this thing is real. On the other hand, if delta phi is imaginary, then in effect I want to get that the change in I want to say that m over square root of lambda plus I epsilon squared doesn't change, and it doesn't change, you see, because it's m squared over lambda plus epsilon squared. So the linear order, it doesn't change. Okay. Whereas if this thing is real, then you have m over square root of lambda plus epsilon real squared. This is m squared over lambda plus 2 epsilon m over square root of lambda. So now there's a linear term. So that's basically why what we have here then is a case where we have one massless particle, one Goldstone boson, and that corresponds to the generator that annihilates the vacuum, and then we have another one. It's not even a generator of the group, it's the vibration in the normal direction, which never was part of the symmetry. And that's still non-zero. So what you've got then is this. To put it differently, mass is basically the resistance that the potential gives to changes in the fields. And so if you have this Mexican hat then, with the water collecting, no, it looks like water. With the water collecting there at the minimum, then a vibration that's this way is resisted because you have to go up in energy. Whereas a vibration in this direction, infinitesimally in that direction, there's no resistance because you're just going along with the water. So that's why the vibrations in this direction, m equals 0, Goldstone, this direction, m greater than 0, or m squared greater than 0, ordinary particle. Okay. That's the second example. All right, let me get the, and what we say is that there's spontaneous symmetry breaking here. What's broken spontaneously is that the vacuum state is one asymmetric choice among a symmetric set of vacua. The vacua is symmetric because the potential and the action have the symmetry. But if we pick one state to expand around it, then we've broken the symmetry. And it's the term, I don't know, I don't like the terminology very much, but I guess it's better than terminology in astronomy where everything's plotted backwards, all the names are historical, and Latin if possible. Even though people don't know how to pronounce Latin or speak Latin, I just anyway, so let's see. I was going to say something. Yes. So it's the state here that would be a state in which the field phi has a mean value equal to m over square root of lambda. This is the complex field. Mean value complex field would be m over square root of lambda. That's what we would call the vacuum. Now, what is the state here? Well, in the old days, people used to think it was an eigenstate of the field, but that's completely ridiculous because, as you know from quantum mechanics, the eigenstate of the position operator has, of course, infinite energy because momentum is totally undefined. And so to here, this is so, it's either the poor man's approximation to this state, and God knows what a real eigenstate is of a real field, but the poor man's approximation is a coherent state. And the coherent state then is an eigenstate of the annihilation operator, or operators, and so it would be the annihilation operator for momentum 0. So A of the 0 on this state would be m over square root of lambda, apart from some overall factor that I'm leaving out. Okay, and the other ones, A of k, 0. Okay. All right, let's go to example 3. Example 3 is like example 1. B of phi is equal to m squared by 1 squared plus r2 squared plus lambda over 2 phi 1 squared plus phi 2 squared squared. Okay. What is the symmetry here? The group G is now equal to U2. And whether the band of that name is named after this group, I don't know. But what is the vacuum? The vacuum is just 0, 0. So the vacuum is simply 0, and any TA on phi 0 is automatically 0, so we're not going to get any Goldstone bosons. The group H that leaves this thing invariant is just equal to G itself. And so what we have then is we don't have any eigens. We just have, if you think of these as real fields, we have four bosons, or scalar bosons of M equal to, you have to compute what the mass is, and the way you compute the mass is you say, well, actually we know what the mass is just of mass M. Because I've written it in such a way that you have mass M. Okay. Equivalently, you have two charged bosons and two anti-charged bosons. All right. Well, not really charged since we haven't gauged it. Okay, now we do example 4, which would be same thing like example 2, but now v phi is minus m squared times phi 1 squared plus phi 2 squared plus lambda over 2 phi 1 squared plus phi 2 squared. Now, this is like the Mexican hat, but in 4 dimensions, so it's hard to visualize. But what we have now is that v of g of phi is equal to v of phi for all g in U2, which is what we had over here. But now, we do have some non-trivial states here. In other words, the minimum of the potential is 0 partial v partial phi squared, by which I mean the sum of these two guys. And this is equal to minus m squared plus lambda phi squared, and so phi 0 squared is equal to m squared over lambda. So what does that mean? That means that, in fact, we've got some extra blackboard, but maybe I should stay here. Phi 0, 1 absolute value squared plus phi 0, 2 absolute value squared is equal to m squared over lambda. So these are all the minimum, these are all possible choices of vacua. And you see it's a huge space because it's the surface of a sphere in 4 dimensions, which I think the mathematicians perversely call S3. But anyway, I don't blame the mathematicians as much as I do the astronomers. At least some logic to the mathematical notation. Okay, let's pick a vacuum. Phi 0 is, I'm going to choose square root of lambda 0, 1. In fact, this is very closely related to the Higgs mechanism. That's why I picked it. So we have 0, 1, and I'm thinking of this as positively charged neutral. But we don't have any gauge field yet. Okay. Now, what is the subgroup that leaves this invariant, or what generators equivalently annihilate it? well, we can take H equal, here's an element of the group, I'm sorry, this is an element of the group. E to the I theta, 0, 0, 1. This is in H, which is contained in G. So this is an element of U2. It's a unitary 2x2 matrix. And on the other hand, it leaves it invariant because H on phi 0 is e to the I theta 0, 0, 1. 0, 1 m over the square root of lambda, and you do the multiplication, you get 0, 1. So you get m over the square root of lambda 0, 1, which is to say phi 0. So here is a whole subgroup. It's a U1 subgroup of U2 that leaves our chosen vacuum invariant. And so whereas U2 has 4 generators, and we would have said, oh, we have 4 Goldstone bosons, we lose 1. So what we have then are 3 Goldstone bosons. I don't know why we don't call them Goldstones, but for some reason that never caught on. Anyway, and 1 massive particle. And to figure out the massive particle, what you've got to do is you choose this as your vacuum, and then you rewrite the potential as V of 0. The linear terms in the change are 0, but then you have to write it as a quadratic form in departures from this phi 0. And then you look at that matrix. That would then be effectively a 2x2 matrix, and you'd see that it would have 3 eigenvectors. No, 1 eigenvector that's non-zero. And that would be you start out with 4 fields, and you don't know what their masses are. You find there are 3 that have mass 0, and 1 has a mass that's something like m over square root of 2m or something. Okay, now let me write down these generators for you of this group U2. I'll write them this way. T1 is a half 0, 1, 1, 0, which is the Pauli matrix. T2 is a half 0 minus I, 0, again a Pauli matrix. But now what we've got is the T3 is just 0, 1, 0, 0, 0, 0, 1. And all of these, so what do I want to say? That's that one. Whereas the generator here is 1, so T4, so to speak. T4 is 1, 0, 0, 0. And you see T4 on phi 0 is 0. So that's the one that's not a Goldstone boson. On the other hand, all of these other guys do move phi 0. So Ti phi 0 is not equal to 0 for I equal to 1, 2, and 3. So these are the Goldstone bosons. All right, I guess we're at the end of the hour. The next thing to do, though, is to consider these 4 theories promoted, in which we promote the symmetry from global. We've been talking only about global symmetry. We promote it from global to local by introducing a gauge field. And in the first two examples, we can just introduce a single gauge field because it's U1 symmetry. In this case, where we have U2, we're going to have to introduce 4 gauge fields. And we'll see we'll see what happens on Thursday. And I have to remember to finish the calculation of the beta function QCD, which I simply forgot to bring. I've got to bring my notes because I forgot about it. I actually wrote the notes up very carefully, but left them in my office because I was thinking about this all weekend. The treatment, by the way, in the Schwartz's treatment of this is much more abstract and difficult to follow. So I think you should pay attention to what I said. You don't need to ignore what he said, but you can read what he said in a more abstract view, more buzzwords and so forth. All right, I guess we can stop. Unless there's a question. No, okay.